252 million years ago, something killed almost everything on Earth. Not a meteor strike, not an ice age, something else. The numbers are hard to wrap your head around. 96% of all marine species gone, 70% of land vertebrates dead. Insects, which almost never go extinct, lost 57% of their families. The only mass extinction that nearly wiped out insects. Scientists call it the Permian-Triassic extinction. Most people call it the Great Dying. Both names work. Because that's what happened. The planet died, not completely, but close enough that life almost didn't come back. Here's what makes it terrifying. We don't fully know why it happened. We have theories, good ones. But the more scientists dig, the weirder it gets. The evidence points in multiple directions. Massive volcanic eruptions in Siberia, ocean chemistry going haywire, methane bursting from the seafloor, global warming that happened too fast for life to adapt. Maybe all of these at once. Maybe something else we haven't figured out yet. The extinction lasted about 60,000 years. That sounds like a long time. It's not. Not in geological terms. For context, modern humans have been around for 300,000 years. This die-off happened 3 times faster than we've existed. Blink of an eye for the planet. An eternity if you're living through it. And here's the thing that keeps scientists up at night. It's happened before, and it could happen again. 5 major mass extinctions in Earth's history. The Permian-Triassic was the worst, but all of them share patterns: climate change, ocean acidification, rapid environmental shifts. Sound familiar? We're watching some of these patterns repeat right now. Slower this time. Maybe, we think. The Great Dying didn't just kill species, it reset evolution. The world before looked nothing like the world after. Trilobites, which had survived for 270 million years, vanished completely. The Synapsids, our distant ancestors, nearly went extinct. Only a few scraped through. Everything that came after, including us, descended from those survivors. Think about that. If a few more species had died, if the extinction had been just slightly worse, you wouldn't exist. None of us would. Different creatures would have inherited the Earth. Maybe no creatures at all. The fossil record from this time is haunting. Layers of rock packed with life. Then a thin boundary layer. Then almost nothing. Just a handful of species clinging to existence. Then slowly, painfully, life crawls back. But it takes millions of years. Scientists have been studying this extinction for decades. They found evidence on every continent. Rocks that tell the same story. Something went catastrophically wrong with Earth's systems. The oceans turned acidic. Temperatures spiked. Oxygen levels crashed. Life suffocated. But the exact sequence, the precise trigger, still debated. And this is where it gets really interesting. Because understanding what killed the Permian world might help us understand what's happening to ours. The patterns echo forward through time. We're not facing another Great Dying. Not yet. But we're running an experiment with our planet's chemistry. Pumping carbon into the air, warming the oceans, acidifying the seas. The Permian extinction whispers a warning across 252 million years. Earth systems have breaking points. Cross them, and the planet doesn't care about your species. It just resets. The world before the Great Dying was strange, alien, nothing like what came after. Picture a supercontinent, all the land masses jammed together into one giant chunk called Pangea. No Atlantic Ocean, no separate continents, just one massive landmass surrounded by one massive ocean. The climate worked differently. The interior of Pangea, thousands of miles from any coast, was a desert. Dry, hot, brutal. But along the coasts and in the south, life thrived. The oceans teemed with creatures we'd barely recognize. Trilobites crawled across the seafloor, They'd been doing this for 270 million years. Successful beyond measure. Brachiopods, which look like clams but aren't, filtered food from the water. Sea lilies, which look like plants but aren't, swayed with the currents. Ammonites spiraled through the depths. Coral reefs stretched for miles. On land, the synapsids ruled. These weren't dinosaurs. Dinosaurs hadn't evolved yet. Synapsids were something else. Our ancestors, actually. Distant ones. They looked like a fever dream crossed between a reptile and a mammal. Because that's essentially what they were. The bridge between cold-blooded and warm-blooded life. Some were massive. Moschops weighed over a ton. Thick skull. Barrel chest. It ate plants and probably couldn't run very fast. Didn't need to. Nothing much hunted it. Asteminosuchus was even bigger. 6 feet tall at the shoulder. Strange bony growths on its head. Scientists still debate what those were for. Display? Fighting? Nobody knows. The predators were equally weird. Gorgonopsids stalked the Permian landscape. These things had saber teeth before saber-toothed cats existed. Long canines for stabbing prey. Some were the size of bears. Fast. Deadly. The apex predators of their time. And then there were the therapsids. Smaller, more varied. Some ate plants, some ate insects, some ate each other. These little creatures, no bigger than rats, would eventually survive the extinction. Their descendants would become mammals, would become us. The forests were strange too. No flowering plants. Those hadn't evolved yet. No grass. The dominant plants were seed ferns and conifers. Glossopteris trees covered the southern parts of Pangea. Their leaves had a distinctive tongue shape. Geologists find these fossils on multiple continents now. Proof that the continents were once connected. The air was different. More oxygen than today. About 30% compared to our 21%. This let insects grow huge. Dragonflies with 2-foot wingspans. Millipedes the size of cars. The extra oxygen supercharged their primitive respiratory systems. But here's the thing. This world was already under stress before the extinction hit. The climate had been shifting for millions of years. Ice ages came and went. Sea levels rose and fell. Species adapted or died. Normal stuff. The churn of evolution. But something was building. Something the Permian world wasn't ready for. In what's now Siberia, volcanoes were waking up. Not normal volcanoes. Something much worse. The Siberian traps. Scientists call them flood basalts. Imagine lava pouring out of cracks in the earth. Not explosive eruptions. Just endless flows of molten rock. Rivers of lava hundreds of feet deep. Covering an area the size of Europe. This had happened before in Earth's history, but never on this scale, never for this long. The eruption started about 252 million years ago. They lasted for maybe 1 million years, on and off, pulse after pulse of lava. Each pulse released gases into the atmosphere, carbon dioxide, sulfur dioxide, chlorine. All the nasty stuff trapped in the Earth's mantle suddenly vomited into the air. The carbon dioxide was the killer. Not immediately. Carbon dioxide isn't toxic at normal levels, but it's a greenhouse gas. It traps heat. The more you pump into the atmosphere, the warmer things get, and the Siberian traps pumped out a lot. Estimates vary. Maybe enough to raise global temperatures by 10 degrees Celsius, maybe more. 10 degrees doesn't sound like much. It's catastrophic. Think about it this way. The difference between an ice age and our current climate is about 5 degrees. Double that, and you're in a different world. Polar ice melts. Sea levels rise. Weather patterns collapse. Ecosystems can't keep up. But it gets worse. The warming triggered feedback loops. This is where the nightmare really begins. Warmer oceans hold less oxygen. Marine life needs oxygen. As temperatures climbed, the ocean started to suffocate. Dead zones spread. Fish died. Invertebrates died. The food chain collapsed from the bottom up, and then there's the methane. Frozen in the seafloor, trapped in ice-like structures called clathrates, sits massive amounts of methane. It's stable when it's cold, but warm the ocean and the ice melts. The methane escapes, bubbles up to the surface, enters the atmosphere. Methane is a greenhouse gas too. Much worse than carbon dioxide, about 25 times more effective at trapping heat. So now you've got a feedback loop. Warming releases methane. Methane causes more warming, which releases more methane. On and on. Scientists found evidence of this. Carbon isotope ratios in rocks from this time show a massive spike in light carbon, the kind that comes from biological sources, like methane from the seafloor. The numbers are staggering. Enough methane to raise temperatures another 5 degrees, maybe more. The oceans turned acidic. When carbon dioxide dissolves in seawater, it forms carbonic acid. A little bit is fine, too much, and the pH drops. The ocean becomes more acidic. This is bad news for anything with a shell or skeleton made of calcium carbonate. The acid dissolves it. Coral reefs died. Brachiopods died. Ammonites struggled. The ocean's entire calcium carbonate cycle broke down. It took millions of years to recover. On land, things weren't much better. The heat was relentless. The interior of Pangea turned into a hellscape. Temperatures in some areas may have hit 140 degrees Fahrenheit. Nothing could live there. Even the coast became unbearable. Plants died. The animals that ate plants died. The animals that ate those animals died. Acid rain fell from the sky. The sulfur dioxide from the volcanoes mixed with water vapour created sulfuric acid. It burned leaves, poisoned soil, killed forests. The ozone layer thinned, maybe disappeared entirely in some places. Ultraviolet radiation bombarded the surface. Mutations increased. Skin cancer in animals. Damage to plant DNA. Another stress piled on top of all the others, and through all of this, life tried to adapt. Some species moved toward the poles, seeking cooler temperatures. But Pangea's geography made this hard. The interior was a barrier. Migration routes were limited. Many species got trapped. Others tried to wait it out, hunker down, survive on less. But the extinction lasted tens of thousands of years. You can't wait that out. Eventually food runs out, water runs out, hope runs out. The fossil record shows the collapse in stages. First, the specialists died. Species adapted to narrow niches, specific foods, specific temperatures. When conditions changed, they had nowhere to go. Then the large animals went. They need more food, more space, more resources. When ecosystems collapse, the big guys go first. Finally, even the generalists struggled. The survivors, the adaptable ones. Because when 96% of marine species are gone, when forests are dead, when oceans are toxic, being adaptable doesn't help much. What's haunting is how close it came to total extinction. A few more degrees of warming, a few more pulses from the Siberian traps, a bit more methane from the sea floor, and maybe nothing survives. Maybe life on Earth ends at 252 million years old. But it didn't. A handful of species made it through. In the oceans, a few mollusks, some fish, hardy invertebrates. On land, small Synapsids, some reptiles, insects, though barely. They inherited an empty world, a blank slate, and slowly, painfully, they began to rebuild. The world they built was different. The Permian world was gone forever. The creatures that survived evolved into new forms. The Therapsids that made it through eventually gave rise to mammals. The reptiles that survived split into different groups. One of those groups became the dinosaurs. Everything that came after traces back to those survivors. Every mammal, every bird, every reptile, all descendants of the few species that refused to die, that found a way through the heat and the acid and the suffocation. We're looking at that world now through layers of rock, reading its story in fossils and chemical signatures, trying to understand what happened, trying to learn from it, because here's what gets me. The Permian world didn't see it coming. The Synapsids didn't know about greenhouse gases. The Trilobites didn't understand feedback loops. They just lived, and then they died. We're different. We can see the patterns. We can read the warnings written in ancient stone. We know what happens when you change a planet's chemistry too fast, when you push systems past their breaking points. The great dying whispers across deep time, not a threat, a memory, a reminder that Earth systems have limits, that life is resilient but not invincible, that worlds can end and new ones can begin. Subscribe for more quiet nights like this. Tell me in the comments, where in the world are you right now? We're separated by thousands of miles and different time zones, but we're all here, thinking about the same vanished world, about trilobites that crawled through oceans for hundreds of millions of years, then disappeared forever, about creatures we'll never see, in forests we can barely imagine. The great dying connects us across time and space, a shared mystery, a reminder that we're all temporary visitors on this planet. Let's talk about numbers, real numbers, the kind that make you stop and think. 96% of marine species died. Think about what that means. If you could line up every creature living in the ocean at that time, only 4 out of every 100 would survive. The rest, gone. On land, 70% of vertebrate species vanished. 7 out of 10 animals with backbones, dead. But here's where it gets worse. The extinction didn't just kill species, it killed entire groups of life that had existed for hundreds of millions of years. Trilobites, completely extinct. Every single species. These creatures had survived 4 previous mass extinctions. They'd crawled across ocean floors since the Cambrian explosion, 521 million years ago. They'd weathered ice ages, volcanic eruptions, asteroid impacts. They'd adapted to warm seas and cold seas, shallow water and deep water. They were survivors until they weren't. The last trilobite died during the Great Dying. After that, the oceans never saw them again. Blastoids went extinct too. These were strange creatures that looked like small flowers made of armor plates. They'd filtered food from the water for 150 million years. All gone. The fusulinids disappeared. These were single-celled organisms, but they built elaborate shells. Some looked like grains of rice, others like tiny footballs. They'd been so successful that their shells formed entire layers of limestone. You can still see those layers today in rocks from the Permian period. But the creatures themselves? Extinct. Rugose corals vanished. These corals had built reefs for 250 million years. They had a distinctive pattern, wrinkle like a brain. They were tough. They'd survived everything the planet threw at them. The Great Dying killed them all. The acanthodians died out. These were some of the earliest fish with jaws. They'd been swimming in Earth's waters for 160 million years. The extinction erased them. Here's what gets me. These weren't weak species barely hanging on. These were successful life forms, dominant, widespread. The kind of creatures you'd bet on to survive anything. They all died anyway. The numbers get more disturbing when you look at specific groups. Take the brachiopods. Before the extinction, there were about 300 genera. After, fewer than 10. That's a 97% loss. Sea urchins lost 98% of their species. Bryozoans, tiny colonial animals that look like moss, lost 79% of their genera. Crinoids, the sea lilies, dropped from 80 genera to just 3. On land, the Therapsids got hammered. These were the dominant land animals, the ancestors of mammals. They'd ruled for millions of years. The extinction killed most of them. Only a few small species survived, hiding in burrows, eating whatever they could find. The Gorgonopsians went extinct. These were the apex predators of their time. Imagine a reptile-like creature the size of a lion, with saber teeth. They were perfect killing machines. Didn't matter. They died with everything else. The Dinocephalians disappeared. The Anomodonts nearly vanished. The Dicynodonts, which had been everywhere, were reduced to just a handful of species. Even the insects suffered. Insects almost never go extinct. They're too adaptable, too diverse, too good at surviving. But during the Great Dying, 57% of insect families died out. That's the only mass extinction that significantly affected insects. The extinction rate was around 90% for all life on Earth. 9 out of 10 species dead. But it's not just about the numbers. It's about what those numbers mean. When you lose 96% of marine species, you're not just losing individual creatures, you're losing entire ecosystems. Food webs collapse, predators starve, prey animals explode in population, then crash when they run out of food. Scavengers multiply, then die when there's nothing left to scavenge. The ocean becomes a different place, not just emptier, fundamentally different. Imagine walking through a forest where 9 out of 10 trees are dead, where most of the birds are gone, where the insects have mostly disappeared, where the streams run empty. That's not a forest anymore. It's a graveyard pretending to be a forest. That was Earth after the Great Dying. The extinction happened in pulses, not all at once. The dying came in waves, each one killing more than the last. The first pulse wiped out maybe 50% of species. Survivors started to recover. Then the second pulse hit. Then the third. Each wave killed species that had survived the previous waves. Species that seemed like they'd make it. Species that had adapted and were starting to thrive again. The pulses came over maybe 60,000 years. That sounds like a long time. It's not. Not in geological terms. Not when you're talking about evolution and adaptation. For comparison, modern humans have been around for about 300,000 years. We've built civilization in the last 10,000 years. The Great Dying happened 3 times faster than human civilization has existed. Life had no time to adapt, no time to evolve new strategies, no time to migrate to safer areas. The killing happened too fast. And here's the thing that really matters. The numbers tell us how bad it was, but they don't tell us why it was so bad. Other mass extinctions killed fewer species. The asteroid that killed the dinosaurs? That took out about 75% of species. Terrible, yes, but not as bad as the Great Dying. The late Ordovician extinction killed maybe 85% of species. The late Devonian extinction got about 75%. The Triassic-Jurassic extinction, which came 50 million years after the Great Dying, killed around 80%. The Great Dying was worse than all of them, by a lot. Why? What made this extinction so deadly? The numbers suggest something went catastrophically wrong with Earth's basic systems. Not just one thing, multiple things, all at once. When you kill 96% of ocean life, you're not just dealing with a bad year, you're dealing with ocean chemistry going haywire, oxygen levels crashing, temperatures spiking, acid levels rising, all of it happening faster than life can handle. When you kill 70% of land animals, you're looking at atmospheric changes, climate shifts, ecosystem collapse on a global scale. When you kill insects, which almost never die in mass extinctions, something is seriously wrong. Insects survive by being adaptable, by reproducing fast, by living in every possible environment. If you're killing insects, you're killing everything. The numbers point to a planet-wide catastrophe, not a regional disaster, not a slow decline, a global emergency that happened too fast for life to escape. Scientists look at these numbers and see a murder mystery. The victim is obvious. Most of life on Earth. The crime scene is clear. Rocks from 252 million years ago found all over the world. The evidence is there. But the killer? That's harder to pin down. The numbers tell us what died. They tell us how bad it was. They tell us how fast it happened, but they don't tell us why. Not completely. That's what makes the great dying so terrifying. We can measure the death. We can count the victims. We can see the devastation in the fossil record. But we still don't fully understand what could kill 96% of ocean life. What could wipe out groups of creatures that had survived for hundreds of millions of years? What could push Earth's ecosystems past the breaking point? The numbers are a warning. They tell us that Earth's systems can fail, that life can come within a hair's breadth of total extinction, that the planet we depend on can turn hostile. And they tell us it's happened before, which means it could happen again. The leading suspect has a name, the Siberian Traps. Traps doesn't mean what you think. It's from the Swedish word trapper, meaning stairs. Because that's what these volcanic formations look like. Giant staircases of cooled lava, stacked on top of each other, stretching across Siberia. But calling them volcanic formations doesn't capture the scale. These weren't volcanoes in the normal sense. No mountain, no cone, no single eruption point. This was something else, something worse. Picture a crack opening in the Earth's crust. Not a small crack, a massive fissure hundreds of miles long, and from that crack lava pours out. Not explosive, just flowing. Endless rivers of molten rock spreading across the landscape like water from a broken dam. The lava flows for thousands of years, layer upon layer, building up, covering an area the size of Europe. 2 million square miles of volcanic rock. That's the Siberian Traps. The timing matches perfectly. The eruptions started right before the extinction. They lasted through the worst of the dying. When you date the rocks, when you measure the isotopes, everything lines up. Scientists started making this connection in the 1990s. They looked at the Siberian Traps and realized the scale. Then they looked at the timing. The pieces fit together. Here's what made these eruptions so deadly. It wasn't just the lava. Lava flows are bad, sure. They destroy everything in their path. But they're local, regional at most. The Siberian Traps killed globally. Because of what came with the lava. Gases. Massive amounts of volcanic gases pumped into the atmosphere. Carbon dioxide, sulfur dioxide, chlorine, fluorine. All the nasty stuff that comes out of volcanoes, but on a scale never seen before or since. The carbon dioxide alone was staggering. Estimates suggest the eruptions released enough CO2 to increase atmospheric levels by 2,000 parts per million. Maybe more. For comparison, we've increased CO2 by about 130 parts per million since the Industrial Revolution. And that's causing measurable climate change. The Siberian Traps released 15 times that amount, maybe 20 times. The planet warmed. Fast. Temperatures rose by 8 to 10 degrees Celsius. Some estimates go higher. In the tropics, summer temperatures might have hit 60 degrees Celsius. That's 140 degrees Fahrenheit. Nothing survives that. Not for long. But the warming was just the start. The sulfur dioxide created acid rain, not light acid rain. Intense corrosive precipitation that fell for thousands of years. It poisoned lakes, killed forests, dissolved shells and bones. The oceans absorbed much of the CO2. That sounds good until you realize what happens when oceans absorb carbon dioxide. The water becomes acidic. Ocean pH dropped. Creatures with calcium carbonate shells couldn't build their shells anymore. They dissolved. That explains why 96% of marine species died. The ocean became hostile to most life. On land, the fluorine and chlorine gases were killers. Fluorine is toxic in small amounts. The eruptions released it in massive quantities. It settled on plants. Animals ate the plants. The fluorine destroyed their bones from the inside. Their teeth fell out. Their skeletons weakened. They died slowly. The evidence for this is in the fossil record. Paleontologists find bones from this period with strange deformities, lesions, signs of fluorine poisoning. But here's where the theory gets complicated. The Siberian traps explain a lot. The warming, the acid rain, the ocean acidification, the poisoning. They explain why so many species died. But do they explain why 96% died? Why this extinction was so much worse than others? Other volcanic events have happened. Big ones. The Deccan traps in India erupted around the same time the dinosaurs went extinct. Huge eruptions. Lasted 1 million years. Released enormous amounts of gas. But the dinosaur extinction only killed 75% of species. Bad, yes, but not as bad as the Permian extinction. Why was the Siberian event so much worse? The location might matter. The Siberian traps erupted through coal beds, massive coal deposits laid down over millions of years. When the lava hit the coal, it burned, instantly, completely. Burning coal releases even more CO2, plus methane, plus toxic compounds. The eruptions didn't just release volcanic gases, they released everything locked in those coal beds. Some scientists think this coal burning doubled or tripled the amount of greenhouse gases released. That would explain the extreme warming. But there's more. The eruptions also went through salt deposits. When lava heats salt, it releases chlorine and bromine. These gases destroy ozone. The ozone layer protects life from ultraviolet radiation. Without it, UV levels spike. Evidence suggests ozone levels collapsed during the extinction. Fossil spores from this period show damage consistent with UV radiation. Plants that survived show genetic changes, mutations from radiation exposure. So life was dealing with extreme heat, acid rain, ocean acidification, fluorine poisoning, and increased radiation. All at once. That's a lot. Maybe enough to kill 96% of species. But some scientists still aren't convinced. They point out that volcanic eruptions happen over thousands of years. Life should have time to adapt, to migrate, to evolve. The extinction happened fast, really fast. The main pulse of dying might have lasted only 60,000 years. Some evidence suggests even faster. Maybe 20,000 years for the worst of it. That's fast for volcanism. Volcanoes don't usually work that quickly, unless something else was happening, something that amplified the volcanic effects. This is where feedback loops come in. Positive feedback loops, which is a terrible name because there's nothing positive about them. Here's how they work. The volcanoes release CO2. The planet warms. Warmer temperatures release more CO2 from other sources. More CO2 means more warming. More warming releases even more CO2. The cycle feeds itself, amplifies, accelerates. One source of feedback was the permafrost, frozen ground in the polar regions. When permafrost melts, it releases methane. Methane is a greenhouse gas 25 times more powerful than CO2. During the Permian, there were no ice caps, but there were areas of frozen ground. The warming from the volcanoes melted that ground, released the methane. The methane caused more warming, which melted more ground, which released more methane. Another feedback was forest fires. The warming dried out forests. Lightning strikes started fires. Fires burned across continents. Burning forests release CO2. More CO2 means more warming. More warming means more fires. The evidence for massive fires is in the rock record. Layers of charcoal, soot particles, signs of burning on a continental scale. A third feedback involved the oceans. This one's complicated but important. Warm water holds less oxygen than cold water. As the oceans warmed, oxygen levels dropped. Marine creatures that needed oxygen died. When they died, they sank to the bottom. Bacteria decomposed the bodies. Decomposition uses oxygen. So you have less oxygen in the water to start with. Then you have dead creatures using up what oxygen remains. Oxygen levels crash. When oxygen runs out completely, different bacteria take over. Anaerobic bacteria that don't need oxygen. These bacteria produce hydrogen sulfide. That's the rotten egg smell. Hydrogen sulfide is toxic, deadly to most life. As it built up in the deep ocean, it eventually reached the surface. It bubbled into the atmosphere. Evidence suggests massive releases of hydrogen sulfide during the extinction, enough to poison the air near coastlines, enough to damage the ozone layer even more. This is the feedback loop from hell. Warming reduces oxygen. Less oxygen means more dead creatures. More dead creatures means more bacteria. More bacteria means hydrogen sulfide. Hydrogen sulfide kills more creatures, which starts the cycle over again. Each feedback loop made things worse, and they all interacted. The volcanoes triggered the warming. The warming triggered the methane release. The methane triggered more warming. The warming triggered ocean anoxia. The anoxia triggered hydrogen sulfide. The hydrogen sulfide killed more life. The dead life made the anoxia worse. The system spiraled out of control. This is what makes the Siberian traps theory so compelling. It's not just about the volcanoes. It's about what the volcanoes triggered. A cascade of environmental disasters, each one feeding into the next. The volcanoes were the match. But the planet was the powder keg. And here's what really gets me. The eruptions lasted maybe 2 million years. But the worst of the extinction happened in 60,000 years, maybe less. That suggests the killing wasn't gradual. It was sudden. A threshold was crossed. A tipping point reached. And once crossed, the system collapsed rapidly. Scientists call this a runaway greenhouse effect. The warming becomes self-sustaining. It doesn't need the volcanoes anymore. The feedbacks keep it going. We see evidence of this in the rock layers. The carbon isotope ratios shift dramatically. Not gradually. Suddenly. Like someone flipped a switch. The oxygen isotope ratios do the same thing. Sharp changes, abrupt transitions, signs of a system in crisis. The Siberian traps theory explains most of this. The warming, the feedbacks, the speed, the global nature of the extinction. But it doesn't explain everything. Some details don't fit perfectly. Some evidence points in other directions. That's why scientists keep digging, keep testing, keep refining the theory. Because understanding what killed 96% of life on Earth matters, not just for understanding the past, for understanding the present. We're adding CO2 to the atmosphere right now, not as fast as the Siberian traps, but faster than at almost any other time in Earth's history except the Permian. We're warming the planet, melting permafrost, acidifying oceans, triggering some of the same feedbacks that amplified the Permian extinction. The Siberian traps theory is a warning. It shows us what happens when Earth systems get pushed too far, when feedback loops start amplifying, when tipping points get crossed. It shows us that extinction doesn't need an asteroid, it doesn't need an ice age, it just needs the planet's basic systems to fail. And it shows us that those systems can fail, have failed, might fail again. The volcanoes didn't mean to kill everything. They were just doing what volcanoes do, erupting, releasing gases, following the laws of geology. But the planet responded. The atmosphere changed, the oceans changed, the feedbacks kicked in, and life paid the price. That's the real lesson of the Siberian traps. It's not about the volcanoes themselves. It's about what they set in motion, the cascade they triggered, the tipping points they pushed Earth past. The planet has limits. Push past them and bad things happen, really bad things. The Siberian traps showed us where those limits are, or at least where they were 252 million years ago. The volcanoes triggered the warming. The warming triggered the feedbacks, but some scientists think there's a missing piece. They look at the ocean, specifically what happened inside it. When water loses oxygen, bad things happen. We touched on this with the hydrogen sulfide, but there's more to the story, more that explains why the ocean became a graveyard. Think about how oceans work today. Surface water mixes with deep water. Currents circulate. Cold water sinks at the poles, carrying oxygen down. Warm water rises at the equator. The whole system moves. This circulation keeps the ocean alive. Oxygen reaches the depths. Nutrients rise to the surface. Life thrives. But during the extinction, this system broke down. The warming changed everything. Warm water at the poles meant less circulation, less mixing. The deep ocean became isolated, cut off from the surface. Without circulation, oxygen couldn't reach the depths, and without oxygen, the deep ocean died. Scientists call this ocean anoxia, water without oxygen. It happens in small areas today. Dead zones in the Gulf of Mexico, parts of the Black Sea. But during the extinction, it happened globally. The evidence is in the rocks. Geologists find black shales from this period. Black shales form in oxygen-free water. They're loaded with organic matter that couldn't decompose because there was no oxygen for bacteria to use. These black shales appear worldwide. In China, Russia, Greenland, Antarctica. Every ocean basin shows the same thing. Oxygen disappeared from the depths. But here's where it gets really interesting. The anoxia didn't stay in the deep ocean, it spread upward. Normally, oxygenated surface water acts as a barrier. It keeps the oxygen-free water trapped below. But as the anoxia expanded, it reached higher and higher in the water column. Eventually, it hit the surface. Evidence suggests that in some areas, the oxygen-free water reached the photic zone. That's the top 200 meters where sunlight penetrates. Where most marine life lives, when anoxia reaches the surface, almost nothing survives. Fish need oxygen, so do most invertebrates. Even plankton struggle. The ocean became layered, oxygenated water at the very top, maybe the first few meters. Below that, nothing. A dead zone extending down thousands of meters. Marine life got squeezed into a thin layer at the surface, overcrowded, competing for limited resources, vulnerable to any further changes. And the changes kept coming. The anoxic water wasn't just lacking oxygen, it was full of toxic compounds, hydrogen sulfide as we mentioned, but also metals like iron and manganese. These dissolved in the oxygen-free conditions. When storms mixed the water layers, these toxins surged upward, poisoning the surface, killing whatever had managed to survive the oxygen loss. Scientists find evidence of this in the chemistry of fossils. Shells from this period show signs of metal poisoning, deformities, abnormal growth patterns, stress markers. The ocean wasn't just low in oxygen, it was actively toxic. But the anoxia theory goes deeper, because oxygen-free oceans don't just kill marine life, they change the entire chemistry of the planet. Oxygen in the atmosphere comes from photosynthesis. Plants and algae split water molecules, release oxygen. This has been happening for billions of years. It's why we have oxygen to breathe. But when ocean anoxia spreads, it kills phytoplankton. These tiny organisms produce about half the world's oxygen. When they die, oxygen production drops. Less oxygen production means atmospheric oxygen levels fall. Not immediately, but over thousands of years the effect adds up. Evidence suggests oxygen levels dropped during the extinction. Not drastically, but enough to matter. From about 30% to maybe 15%. That's a rough estimate. The numbers are debated. Lower oxygen makes life harder, especially for large animals. They need more oxygen to fuel their bodies. When oxygen drops, they struggle. On land, this meant insects got smaller. Flying takes a lot of energy, need a lot of oxygen. Big insects couldn't survive in lower oxygen conditions. In the ocean, it meant fish had to stay near the surface, had to keep moving to get enough oxygen. Exhausting, unsustainable. The anoxia didn't just kill directly. It created conditions where survival became nearly impossible. And here's the feedback loop. Dead organisms sink. Bacteria decompose them. Decomposition uses oxygen. More death means more decomposition. More decomposition means less oxygen. Less oxygen means more death. The system fed itself, spiraled downward. Scientists can track this spiral in the rock layers. They measure carbon isotopes. During normal times, the ratio of carbon-12 to carbon-13 stays relatively stable. But during the extinction, the ratio swings wildly. These swings indicate massive changes in the carbon cycle. Huge amounts of organic matter being produced and buried, then released, then buried again. The system was unstable, chaotic. The ocean was dying, and as it died, it released more carbon. More carbon meant more warming. More warming meant less oxygen. Less oxygen meant more death. Another feedback loop, another amplifier. But the anoxia theory has a problem. Ocean anoxia happens in other mass extinctions. The Triassic extinction, 201 million years ago. The Torsion extinction, 183 million years ago. Both involved ocean anoxia, but neither killed 96% of marine species. They were bad, but not this bad. So what made the Permian anoxia so much worse? Some scientists think it's about duration. The anoxia lasted longer during the Permian, maybe 1 million years. Other anoxic events lasted tens of thousands of years, maybe 100,000. Longer duration means less chance for recovery. Ecosystems that might bounce back from 50,000 years of anoxia collapse under 1 million years. But other scientists aren't convinced. They point out that life is resilient. 1 million years is a long time. Species should adapt. New ones should evolve. Unless the anoxia kept getting worse, kept expanding, never gave life a chance to stabilize. This is where the theory gets complicated. Because the anoxia wasn't constant, it pulsed, came in waves. The rock record shows this. Layers of black shale alternate with layers of normal sediment. Anoxia spreads, then retreats, then spreads again. Each pulse worse than the last. Life tries to recover after each retreat. Populations start rebuilding. Then the next pulse hits, wipes out the survivors. This pattern of repeated crises might explain the extreme death toll. Life never got a chance to fully recover. Each wave hit a weakened ecosystem, pushed it closer to total collapse. Scientists call this a press-pulse extinction, a long-term press of bad conditions, punctuated by pulses of acute crisis. The press was the warming and the initial anoxia. The pulses were the expansion events, each one spreading the dead zones further, reaching shallower water, killing more species. The evidence for this pattern is strong. Geologists can count the pulses in the rock layers. At least 5 major expansions of anoxia, maybe more. each one leaving a mark in the sediments. Each pulse corresponds with a spike in extinction rates. More species disappearing. More families going extinct. The correlation is clear. But what caused the pulses? Why did the anoxia expand in waves rather than gradually? One possibility is the methane. We talked about methane release from permafrost and seafloor deposits. That methane didn't release smoothly, it released in bursts. Each burst of methane caused rapid warming. Rapid warming reduced ocean circulation. Reduced circulation expanded the anoxia. The anoxia killed more life. Dead life released more carbon. More carbon triggered more methane release. Another feedback loop, another amplifier, but this one operated in pulses. Discrete events separated by recovery periods. The ocean chemistry supports this. Isotope ratios show sudden shifts, sharp changes in carbon, oxygen, and sulfur isotopes. These shifts mark the pulses, the moments when the system lurched toward collapse. Between the pulses, the ratios stabilize. Not back to normal, but stable, suggesting brief periods when things weren't getting worse, when life could catch its breath. Then the next pulse would hit. This pattern of crisis and recovery eventually broke the ecosystem. The recoveries got weaker, the crises got stronger, until finally the system couldn't recover anymore. The ocean had become too toxic, too oxygen poor, too warm. Life couldn't adapt fast enough, couldn't evolve solutions, couldn't find refuges. The anoxia theory explains this pattern. The volcanic gases triggered the warming triggered the anoxia triggered the pulses. The pulses killed 96% of marine species. It's a compelling explanation. It fits the evidence. It accounts for the severity. It explains why the ocean died so completely. But it raises another question. If the ocean became anoxic, how did anything survive? 4% of marine species made it through. That's not many, but it's not zero. Something survived. Something found a way. Scientists think the survivors lived in specific refuges, areas where oxygen persisted, maybe coastal regions with strong currents, maybe cold water pockets at high latitudes, maybe shallow lagoons with lots of algae producing oxygen. These refugees were small, isolated, but they kept life going. Barely. The survivors were generalists, species that could tolerate a wide range of conditions, that could eat different foods, that could handle low oxygen and high temperatures. Specialists died. Creatures adapted to specific conditions had nowhere to go when those conditions disappeared. Coral reef species, deep-sea creatures, anything with narrow requirements. The survivors rebuilt the ocean, slowly, over millions of years, but they rebuilt it differently. The new ocean had different dominant groups, different ecological structures, different rules. The ocean before the extinction was ancient, stable, dominated by groups that had ruled for hundreds of millions of years. Trilobites, certain types of brachiopods, rugose corals. The ocean after the extinction was modern, dynamic, dominated by groups that had been minor players before. Mollusks, modern corals, fish. The anoxia theory explains this transition. It explains why the old groups died and the new groups survived. The old groups were specialized, adapted to stable, oxygenated conditions. The new groups were flexible, could handle instability. The extinction was a filter. It filtered out stability-adapted life, left only the flexible survivors, and those survivors inherited an empty ocean, a blank slate. They diversified rapidly, evolved into new forms, filled the vacant ecological roles. This is why the extinction matters, not just because it killed so much, but because it reset the ocean, changed which groups dominated, set the stage for everything that came after, including us. Because the survivors included the ancestors of fish, and fish eventually gave rise to amphibians, and amphibians gave rise to reptiles, and reptiles gave rise to mammals, and mammals gave rise to us. If the anoxia had been complete, if nothing had survived, if the ocean had stayed dead, we wouldn't be here. The 4% that survived made all the difference. They were the seed, the remnant, the beginning of the next chapter. The anoxia nearly ended the story, but not quite. Life held on, in tiny refuges, against impossible odds. And from that tiny remnant, the whole modern world evolved. So we've traced the chain of disasters. Volcanoes erupt, temperatures rise, oceans lose oxygen, life gets hammered by wave after wave of bad news. But even after all that, there's still a puzzle left. Some scientists look at the data and say, this is huge, but it doesn't explain everything. It's like solving a giant jigsaw puzzle and realizing a few key pieces are missing. Something else, maybe something stranger, pushed Earth to the edge. Here's where things get weird. The main culprits, volcanoes, global warming, poisoned oceans, are big enough on their own. But the numbers don't quite add up. Other mass extinctions had some of these things too, yet none wiped out life so completely. Why did everything hit so hard all at once, at this exact moment in history? What flipped the switch from bad to almost the end of all life? This is where the idea of a cosmic trigger comes in. It's a theory, not a proven fact, but it's a reminder that sometimes the universe can throw in a wild card, something nobody expected. Something from space. Let's start with the most dramatic idea, an asteroid or comet impact. The image pops up every time we talk about mass extinction. A space rock bigger than a city slams into Earth. The impact throws dust into the air, fires rage, darkness falls. Life struggles to survive in a world gone cold and dark. This exact thing happened 66 million years ago. That's what killed the dinosaurs. The asteroid that hit what's now Mexico left a crater 90 miles wide. It was a disaster, but it left behind a smoking gun, actual proof in the rocks, a layer full of iridium, a rare metal from space, melted glass beads, shocked quartz, formed under high pressure. So did something like this happen at the end of the Permian period? Here's the tricky part. Scientists have looked for the same clues, evidence of a giant impact. They've searched for craters, for spikes of rare metals, for the fingerprints that say, yes, something from space hit us. And honestly, they haven't found anything as clear as the dinosaur-killing impact. There are some odd signals, though. In some parts of the world, rocks from the right time show tiny grains of shocked quartz. Some places have little bits of nickel and chromium that seem out of place. Some researchers even claim to have found traces of fullerenes, strange molecules that can trap gases from space. Is that enough to blame an asteroid? Most scientists say no. The evidence is thin, scattered, not as convincing as that dinosaur event. There's no giant crater, no clear global layer of space dust. If something hit Earth, it wasn't as obvious, or maybe it landed in the ocean and left no trace we've found yet. But let's not rule it out completely. Some scientists say maybe the impact was smaller, or maybe it was part of a 1-2 punch. Imagine a comet or asteroid hits, not big enough to kill everything outright, but strong enough to shake things up. Maybe it triggers the volcanoes, or shakes loose methane from the seafloor. Maybe it's the spark that sets off all the other disasters. In that case, the cosmic trigger is more like the first domino in a long, terrible chain. It's a mystery. The evidence is there, but it's faint, like a whisper from deep time. There's another cosmic theory, one that gets even stranger. What if the disaster came not from a rock, but from a burst of energy? Not an explosion on Earth, but a blast from space. Think about the sun. It sends out solar flares, huge bursts of radiation. Most of the time, Earth's magnetic field blocks the worst of it. But sometimes, the Sun has what's called a superflare, something much, much bigger than anything we've seen in modern times. If one hit Earth, it could strip away the ozone layer, flood the planet with ultraviolet light, and make life on the surface really dangerous. Here's what gets me. We don't actually know if the Sun's ever done this. We've only watched it closely for a few hundred years. But stars like the Sun sometimes do have superflares, at least from what astronomers see on distant stars. If it happened once in our past, it could explain a sudden, sharp crisis. There's no direct evidence for a superflare at the end of the Permian, but it's possible. A blast of radiation could have killed plants on land, stressed animals, and changed the chemistry of the atmosphere. It could have helped push an already stressed world over the edge. If not the Sun, maybe something even more exotic, like a gamma-ray burst. These are the most powerful explosions in the universe, caused by stars collapsing or colliding. If one happened close to Earth, even for just a few seconds it could wreck the atmosphere. Gamma rays break up nitrogen and oxygen, making chemicals that destroy ozone. Without ozone, ultraviolet radiation pours in. That could mean mass death for plants and animals, especially those on land. Again, this is a wild idea. There's no physical evidence for a gamma-ray burst in Earth's past, but it's not impossible. The universe is a dangerous place. Sometimes, strange things happen. Let's take a step back. Why do these cosmic theories keep coming up, even when the evidence is thin? It's because the end Permian extinction is so extreme. The usual suspects, volcanoes, warming, anoxia, explain a lot, but the scale of death is hard to match. Some scientists think there must be something else, a final push, a trigger from outside our world. There's a third idea too. This one isn't about rocks or radiation. It's about cosmic rays, high-energy particles from deep space. These rays zip through the galaxy at nearly the speed of a light. Most of the time, Earth's magnetic field and atmosphere protect us. But if something changed, like if the solar system drifted through a dense cloud of cosmic rays, or if a nearby star exploded, the extra radiation could have strange effects. Some researchers think a spike in cosmic rays could change the climate. Cosmic rays can help make clouds, which affect how much sunlight reaches the ground. Too many clouds, and the planet cools down. Too few, and it heats up. Or cosmic rays could cause more lightning, which could spark wildfires. Fires release carbon dioxide, change plant life, and stress animal populations. The problem, again, is evidence. We can't dig up a fossil and say, this was killed by cosmic rays. But some ancient rocks show weird patterns of certain isotopes, forms of atoms that can change when hit by radiation. These patterns might be a clue, but nobody agrees on what they mean. So if a cosmic trigger happened, it's hiding well. The clues are subtle, not obvious. Let's look at another puzzle. The timing. The extinction didn't happen as one single event. It was a drawn-out crisis with ups and downs. But some data shows sudden, sharp jumps in death rates, almost as if something big and fast happened, mixing with the slower disasters. That's another reason people look for a cosmic trigger. Sometimes Earth's disasters are drawn out. Other times they're sudden. Did something from space set off one of these sharp drops in life? There's another angle too. Earth's own cycles. The planet isn't just a passive target. It moves through the galaxy. The solar system bobbles up and down as it orbits the center of the Milky Way. Some scientists wonder if these movements push us through dangerous patches, dust clouds, radiation belts, or even just parts of space that mess with our climate in ways we barely understand. Maybe, every so often, Earth's journey through space lines up with disaster. Now, these ideas are all in a way long shots. But the reason they stick around is because something about this extinction just doesn't fit the normal pattern. Let's pull all the threads together. What if the real answer isn't one single cause? Maybe it's a perfect storm of disasters. Volcanoes erupt, huge ones. The planet heats up. Oceans turn toxic. Life is already stretched to its breaking point. Then, maybe, an extra shock comes from space. A comet, a burst of radiation, a spike in cosmic rays. Not enough to kill everything on its own, but enough to push life over the edge. In that case, the cosmic trigger isn't the main character. It's the final straw. And this is where science gets tricky. The deeper you look, the more you realize how many things have to go wrong for a disaster like this. Earth's history is full of crises, ice ages, asteroid hits, volcanic winters. But the end Permian extinction stands out because all the bad things seem to happen together. The cosmic trigger theory reminds us that while we understand a lot, there's still so much we don't know. The rocks tell us part of the story. The chemistry tells us more, but some pieces might be lost forever. Or maybe someday a new discovery will give us the missing clue. It's a little humbling. We're used to thinking we can figure anything out if we dig long enough, or run enough tests, but some mysteries are stubborn. Sometimes the universe doesn't leave a clean trail. Still, these theories matter. Not just because they're wild or dramatic, but because they make us look up. They remind us that Earth isn't alone. We're part of a bigger cosmos. Space isn't just empty darkness. It's full of dangers and surprises. If a cosmic event really did play a role, even a small one, it changes how we see our own story. It means life on Earth depends not just on what happens here, but on things happening millions or even billions of miles away. And here's something else to think about. These cosmic events, rare as they are, could happen again. The odds are low, but not zero. The same goes for giant volcanoes, or sudden shifts in climate, or oceans losing their oxygen. Earth has always been a place of risk. Life survives by adapting, by hanging on through the disasters. So why does this all matter? Why spend so much time wondering about cosmic triggers and lost worlds? Maybe it's because it shows how fragile things can be, how a planet full of life can be pushed to the edge by a mix of disasters, some from deep inside, some from far away. But it also shows how tough life is. Even when everything goes wrong, something survives. A few tough species in the right place at the right time. They hang on, rebuild, and start the story again. The cosmic trigger theory might never be proven. Maybe we'll find a crater under the ocean, or a hidden layer of space dust, or a pattern in the rocks that finally settles the debate. Or maybe not. Maybe the real lesson is that Earth's history is built on both chaos and luck. We like to look for clear answers, one cause, one effect. But sometimes the truth is messier. The end Permian extinction is like that. It's a mix of volcanoes, climate, oceans, and maybe, just maybe, a little help from space. If nothing else, these theories keep us humble. They remind us not to take life for granted, not to assume things will always be the way they are now. So the next time you look up at the night sky, remember, Earth's story isn't just written in rocks and fossils, it's written in the stars too. And that's what makes this mystery so compelling. We may never know exactly what happened, but by searching, by piecing together clues from the ground and the sky, we get a little closer. Whatever the cause, life found a way through. The survivors made it, and from them, everything else followed. After all that destruction, you'd think nothing could have survived. The world was almost empty. Oceans turned poisonous. Forests burned or dried up. The sky was probably full of haze, making daylight weak and strange. Most creatures vanished. But here's what's wild. Some life forms managed to pull through. They squeezed by, holding on through the worst disaster Earth ever saw. Let's look at who survived, how they did it, and what set them apart from everything else. Because the survivors weren't just lucky. They had traits, habits, or quirks that gave them an edge. And understanding those survivors isn't just about listing names. It's about figuring out why life didn't end for good. To start, picture what was left. The land was mostly bare. Swamps and forests had shrunk or turned to dead zones. Rivers ran muddy and full of debris. The air was hot, sticky, and probably smelled of sulphur. In the ocean, dead zones stretched for miles. The water was warm and low on oxygen. The currents that used to keep everything mixed and fresh had stalled. Into this world stepped the survivors. They weren't the biggest or the most impressive. The mighty reptiles and giant bugs were gone. The weirdest, oldest sea creatures disappeared. What remained were the hardiest and the most adaptable. Let's start underwater, because the ocean took the hardest hit. Nearly everything died, but not quite everything. Some groups of animals managed to make it. For example, there were tiny shelled creatures called brachiopods. Most went extinct, but a few stubborn species held on. They lived in places with just enough oxygen to get by. Some dug into the mud, hiding from the worst surface conditions. Others survived in shallow water, where the waves churned up more air. There were also bivalves. Think clams and oysters. These creatures could close up tight when things got bad. When the water turned toxic, they sealed their shells and waited. That trick alone probably saved their line. Today's clams and mussels are their descendants. Another group that made it were the ancestors of modern snails. Some of them could handle low oxygen. They scraped food off rocks so they weren't picky eaters. Some lived in burrows, out of reach of the worst poisons. Others could go dormant, basically hibernate, when things were too rough. Not a glamorous life, but it worked. There's also the story of the ammonoids. These were relatives of today's squids and octopuses, but with coiled shells. Most ammonoid species disappeared, but a tiny handful made it through. Scientists still aren't sure why. Maybe they lived deeper or in cooler water, or maybe they just got lucky with their timing. Either way, their survival meant that the line of coiled shell cephalopods continued for a while, longer, until their final end much later. Let's not forget the fish. Most big fish died off, but some small, tough species lived on. Lungfish are a great example. These fish could breathe air if the water lost oxygen. That gave them a huge advantage. When other fish suffocated, lungfish gulped air and waited for better times. Their kind still exist today, hiding in muddy riverbeds in Africa, South America, and Australia. Sharks are another group that squeaked through. They weren't immune to the disaster, many types vanished, but a few types survived. The survivors were usually small, adaptable, and able to eat many different foods. Flexibility was key. Switching to land, things looked just as grim. Most large animals were wiped out, especially the big amphibians and reptile-like creatures that had ruled for ages. But a few lines found ways to survive. One group was the ancestors of modern reptiles. Some of these were small creatures that could live in burrows. Living underground protected them from heat, fires, and bad air. Burrowing animals had a better shot at survival, not just because they avoided the worst surface conditions, but also because the ground stayed cooler and more stable. There were also early relatives of mammals. Scientists call them cynodonts and dicynodonts. These names sound a bit silly, but they matter. Cynodonts were small, fast, and possibly warm-blooded or close to it. They might have had fur. Some could eat a wide range of foods. Dicynodonts were more like stocky plant-eaters with beak-like mouths. Both groups had species that survived by being small, hiding out, and not needing much to eat. Here's something interesting. Being small was a big advantage. Small animals need less food. They can find shelter more easily. They also reproduce faster, so even if most of the population dies, a few survivors can quickly rebuild their numbers. The world after the extinction was a place for survivors, not rulers. Plants had their own winners and losers. Forests collapsed in many places. Giant trees died off. But some plants bounced back. Ferns, for example, love disaster. They produce huge amounts of spores and can colonize bare ground fast. In rocks from right after the extinction, there's a fern spike, a sudden jump in fossil fern spores. It's like nature's reset button. The forests are gone, so ferns rush in and take over for a while. There were also some hardy seed plants that survived. These could handle dry, hot or salty soils. They didn't need perfect conditions. Some grew quickly and spread fast, filling empty spaces left by dead trees. Over time, these tough plants would help restart the world's forests. Let's take a closer look at why certain animals and plants survived. What traits made the difference? One big factor was tolerance for bad conditions. Animals and plants that could handle heat, drought or low oxygen had a much better chance. If you needed rich soil, clean water or stable weather, you were probably doomed. Another key was flexibility, what scientists call being a generalist. If you could eat many kinds of food, live in many places, or survive both wet and dry spells, you had a shot. Specialists, animals that needed one exact food or a certain climate, mostly vanished. Timing also mattered. Some creatures survived because they could reproduce quickly. If you can lay lots of eggs, or have many babies in a short time, your group can bounce back fast even after a disaster. Burrowing was another lifesaver. Living underground protected animals from heat waves, wildfires and bad air. It was like having your own bunker during the worst days. Some of the first mammals, as well as some reptiles and amphibians, probably spent a lot of time hiding in the soil. Fossil burrows from this time show that life underground was a winning strategy. Then there's the story of the Lilliput effect. After big extinctions, many surviving animals are smaller than their ancestors. It's named after the island of tiny people in Gulliver's Travels. Small size uses less energy, needs less food, and lets you grow up faster. In the harsh world after the disaster, being small was a ticket to survival. Now let's talk about the survivor's world. It wasn't a paradise, it was more like a wasteland. For thousands of years, Earth looked strange and empty. Fossils show weird patterns. In many places there are layers and layers of rocks, with almost no fossils at all. Scientists call this the dead zone. It's a time when almost nothing left behind a trace. Where fossils do appear, they tell us about a world in recovery. In the ocean, the first creatures to come back in big numbers were simple ones. Tiny clams, worms, and the ancestors of shrimp and crabs. Coral reefs, which had covered huge areas before, were gone. It took millions of years for new reefs to form. On land, the first big comeback was the disaster fauna. That's the name scientists give to the small, tough animals that filled the empty spaces. They weren't impressive. No dinosaurs yet. Just lizard-like reptiles, small amphibians, and those early mammal relatives. They lived fast, died young, and filled every little crack in the ecosystem. Plants also staged a slow recovery. Ferns and simple seed plants came first. Later, as soils improved and the climate became less extreme, forests returned. But it took a long time. There's a gap in many places, sometimes called the coal gap, where no coal formed, because there weren't enough big plants to make peat bogs. That gap lasted for millions of years. Let's dig deeper into some specific survivor stories. One is the Lystrosaurus. This animal looked a bit like a pig with a beak. It was a decinodont, a plant eater with 2 tusks and a stubby body. Lystrosaurus didn't just survive, it thrived. In rocks from right after the extinction, Lystrosaurus fossils are everywhere. Some places have nothing else. It spread from what's now South Africa to Russia, China, and even Antarctica. How did it do it? Probably by being tough, not picky, and able to live in burrows. It could survive on dry, rough plants. It was the ultimate generalist. In the ocean, one survivor was the microconchid. This was a tiny tube-dwelling animal, maybe related to worms. They lived on almost any surface: rocks, shells, even dead bodies. When everything else was gone, microconchids covered the seafloor. They were the first to show up in the new, empty world. Another ocean winner was the bivalve Clarea. This clam lived in muddy, low-oxygen water. Its fossils are found all over the world, sometimes packed together in huge numbers. The secret? Clarea could live where almost nothing else could. It didn't need much oxygen. It didn't care if the water was warm or salty. It just kept going. Let's not forget the first archosaurs, the group that would later give rise to crocodiles and, much later, dinosaurs. The earliest archosaurs were small, fast, and probably ate anything they could catch. By being flexible and quick to adapt, they found a place in the New World. Even insects had their survivors. Most giant insects died out, but smaller types survived. Cockroaches, for example, are famous for being able to live through almost anything. That reputation started early. It's easy to look back and think survival was all about luck. But the fossils tell a more complicated story. The survivors weren't just lucky. They had the right mix of traits: toughness, flexibility, small size, the ability to hide or hibernate, the willingness to eat whatever was available. Scientists have found clues in the rocks that show just how harsh life got for these survivors. Fossilized bones and shells from after the extinction often show signs of stress. Growth rings, like those in trees, are tightly packed, showing slow growth and hard times. Some bones are deformed, probably from disease or lack of food. Shells are thin or twisted, signs of poor nutrition. There are also signs that the survivors lived in strange places. In some fossil beds, the only animals found are those that lived in burrows, or in places with flowing water. It's like the rest of the world was off limits for a while. Another clue comes from the patterns of extinction and recovery. In many places, there are several waves of death and rebirth. A few species come back, then get wiped out again. It's like trying to light a fire in the wind. It keeps getting blown out. Only the most persistent forms of life finally took hold. So, what does all this mean? Why does it matter who survived? First, it shows that life is stubborn. Even when almost everything goes wrong, something finds a way. The survivors after the Permian extinction weren't the most impressive or beautiful. They were the ones who could take a beating and keep going. Second, it tells us about how evolution works during crisis. Big disasters reset the board, old winners disappear, new groups get a chance. The creatures who survived the worst times didn't just go back to normal. They changed, adapted, and started new lines that would shape the world for millions of years. Third, it's a reminder that survival isn't about being the strongest or the smartest. Sometimes it's about being flexible, about finding shelter, eating anything, or waiting out the storm. That's a lesson that still matters. And finally, the story of the survivors gives us a picture of what it really means to start over. After the extinction, The world was open, empty spaces everywhere. The survivors spread out, tried new things and filled the gaps. That's how we got the first dinosaurs, the first mammals, and much later, the first flowering plants. So when you look at a clam, a cockroach, or a fern, remember, they're not just leftovers, they're champions. They made it through the worst time Earth ever experienced. But surviving was just the beginning. Recovery was slow. It would take millions of years before life really bounced back, and the world filled up with new forms. The story of starting over is its own epic, and that's where we're headed next. So, how long did it really take for Earth to recover after almost everything died? If you're hoping for a quick comeback, you might want to lower your expectations. The numbers are almost hard to believe. After the end Permian extinction, life didn't just bounce back in a few years, or even a few thousand. It took a stretch of time that's hard to picture. You could fit all of human history from the first stone tools to today into just a small part of that recovery. Let's start by painting a picture of what recovery even means after a disaster this big. Imagine a world where almost every type of animal is gone. The oceans are quiet, forests are missing. The air, land and water are all out of balance. After the worst was over, life had to do more than just survive. It had to rebuild. It wasn't about getting back to normal. It was about inventing a whole new normal from scratch. Right after the extinction, the world was stripped down to the basics. In the first few thousand years, life was barely hanging on. If you look at the rocks from this time, you see something stark. Layers with almost no fossils. Scientists call these dead zones. It's not just that the big animals are missing. Even the small, simple creatures are rare. In some places, you can go through meters of rock, representing thousands of years, and find almost nothing. It's as if the world pressed pause. This wasteland phase didn't last forever, but it lingered. In the ocean, the first signs of recovery came from simple animals. Tiny clams, tube worms, and other creatures that could handle terrible conditions started to show up in the fossil record. These weren't the same as the rich, complex communities that had filled the seas before. Instead, it was a bare-bones lineup, just a few tough species, making do with what little was left. On land, things moved just as slowly. Plants had to come back before animals could. At first, the ground was probably covered with bare dirt, mud, and scattered ferns. Forests were gone in many places. Where trees had once grown, there might be just stunted plants and rocks. Over time, simple plants like ferns and club mosses spread out, making the ground a little less empty. But big forests? Those were still far in the future. So how do scientists measure recovery? It's not just about counting species. They look for clues in rocks and fossils. One big clue is the return of complex ecosystems. Places where many different animals and plants live together, eat each other, and shape the environment. Before the extinction, the world's ecosystems were rich and layered. Afterward, they were flat and simple. Let's look at some numbers. Studies show that in many parts of the world, it took at least 3 to 5 million years before the oceans had anything close to their old variety of life. And even then, things were different. Some groups that had been common before never came back. Coral reefs, for example, vanished almost everywhere. For a long stretch after the extinction, no true coral reefs formed at all. Instead, the ocean floor was covered with simple mats of bacteria and algae. The first true reefs didn't reappear for another 10 million years or more. On land, the story is just as slow. Fossil evidence tells us that big forests were missing for about 5 to 10 million years in many regions. Instead, plants like ferns and small seed plants dominated. These acted like pioneers, spreading across empty ground, but they couldn't build the deep, rich soils that forests need. Now think about animal life. After the extinction, most land animals were small and simple. The so-called disaster fauna ruled. A handful of tough, fast-breeding species that could survive almost anywhere. Lystrosaurus is a famous example, but it wasn't alone. For millions of years, these simple animals filled the land with almost nothing challenging them. It was a world of survivors, not winners. Why did it take so long for new animals to appear? Part of the answer is climate. After the extinction, the world stayed hot, dry and unpredictable for a long time. The air was full of carbon dioxide. Rainfall patterns shifted. Soils were poor. All of this made it hard for new plants and animals to get established. Even when things started to cool down a bit, the damage had already slowed everything to a crawl. Let's zoom in on the oceans for a moment. Scientists look for certain markers in rocks to track recovery. One is the appearance of bioturbation. That's a fancy word for animals digging and stirring up the mud. Before the extinction, the seafloor was full of life. Worms, clams and other creatures dug into the mud, mixing things up. Afterward, the mud was mostly untouched. It took about 5 million years before animals started digging in large numbers again. Another marker is the return of predators. Before the disaster, oceans had a whole food web, from tiny plankton to giant sea reptiles. Afterward, most predators were gone. It took several million years for new ones to show up. At first, the food chain was short, just a few steps from plants to small animals. Only much later did bigger, more complex predators return. On land, you can see a similar pattern. After the extinction, there were almost no big meat-eaters. The top predators were small, quick reptiles and the ancestors of mammals. Only after ecosystems grew more stable did larger predators appear. Let's talk about the coal gap. This is a period when almost no coal formed anywhere on Earth. Coal forms from dead plants piling up in swamps and forests. Before the extinction, there were huge coal beds being made all over the world. Afterward, almost nothing. For about 10 million years, there's a gap in the record, a sign that big forests just weren't there. What about the return of diversity? That's another way scientists track recovery. Before the extinction, there were thousands of kinds of animals and plants. Afterward, only a handful. It took more than 10 million years for the number of species to climb back up to anything close to what it had been. Now, here's where it gets really interesting. The animals and plants that did return weren't the same as before. The recovery wasn't just a rewind, it was a reset. New groups took over. On land, the survivors gave rise to the first true archosaurs, relatives of crocodiles and dinosaurs. In the sea, new types of shellfish and fish appeared. You might wonder, why did recovery take so long? Why didn't life just snap back the way it does after a forest fire or a volcanic eruption today? Scientists have a few ideas. First, the disaster changed the climate and the chemistry of the planet for a long time. The air stayed warm and full of greenhouse gases. The oceans stayed low in oxygen. Even after the worst was over, the world was still tough for life. There were more heat waves, more drought, and more toxic chemicals than before. Second, the survivors were generalists, animals and plants that could live almost anywhere, but didn't create complex ecosystems. These disaster species kept things simple. They bred fast and took over empty spaces, but they didn't build the kind of rich environments that let other species thrive. It's like weeds taking over an empty lot. They cover the ground, but they don't make a forest. Third, there were repeated setbacks. In some places, the fossil record shows that life started to recover, then crashed again. These recovery failures might have been caused by sudden climate swings, more volcanic eruptions, or even brief returns of toxic ocean conditions. Every time life started to get going, something would knock it back down. Let's look at an example from the ocean. For a long time after the extinction, most animal fossils come from shallow coastal areas. Deeper water stayed almost empty. Scientists think that it took millions of years for oxygen to reach the deep sea again. Until then, only the hardiest animals could live there. On land, recovery was also patchy. Some regions bounced back faster than others. In places where the climate was a bit milder, or where soils recovered sooner, forests and animals returned first. Other areas stayed barren for ages. Here's an example from South Africa. Fossil beds there show that after the extinction, Lystrosaurus was almost everywhere. For a while it made up 90% of all land animal fossils. That's a level of dominance you almost never see. Over time, new animals started to appear, small reptiles, early archosaurs, and the ancestors of mammals. But it took several million years for this simple community to get more complex. Let's not forget about plants. After the ferns, hardy seed plants took over in many areas. These plants could handle dry, poor soils. They spread quickly and made the first steps toward rebuilding forests. But the forests that finally did return looked different from before. New types of trees and shrubs appeared. Some were ancestors of today's conifers, like pines and firs. Others were early relatives of flowering plants, though true flowers wouldn't show up until much later. Over time, as the world stabilized, new animal and plant groups took the lead. On land, the early archosaurs evolved into the first true dinosaurs. Mammal ancestors started to branch out, though they stayed small for a long while. In the ocean, new groups of fish, shellfish, and even early marine reptiles began to fill the empty spaces. By about 15 million years after the extinction, the world was transformed. Entirely new ecosystems had formed. Coral reefs had returned in some places, built by new types of corals. Forests covered much of the land again, though with different trees than before. The animal kingdom was full of new faces, creatures that would go on to shape the next era of Earth's history. What does this long, slow recovery tell us? First, it shows that life is tough, but not invincible. When the world is knocked off balance, it doesn't just go back to the way things were. It changes, sometimes in ways that can't be undone. Second, it's a lesson in patience. The time it took for life to recover is almost beyond human understanding. If you started counting seconds from the end Permian extinction until recovery, you'd never finish in your lifetime. You could count for generations and still not reach the end. Third, recovery isn't just about numbers. It's about complexity. Before the extinction, the world was full of connections, plants, animals, fungi, and bacteria all tangled together in webs of life. After the disaster, those webs were torn apart. It took millions of years to weave them back together. Here's something else to think about. Even when life came back, it wasn't the same. The old champions were gone. New groups took over. It's a reminder that every disaster, no matter how terrible, is also a beginning. Out of the ashes, something new always finds a way. Scientists still study the rocks and fossils from this time, looking for clues about how recovery worked. They use everything from chemical tests to computer models to piece together the story, but there are still big questions. Why did some places recover faster than others? Why did some groups reappear quickly, while others took much longer? Was it just chance? Or did certain traits make the difference? And here's the thing. Earth has never had a disaster quite like this one again. Later extinctions were bad, but not as complete. The end Permian extinction set the bar for just how much life could be lost and how slowly it could come back. So, when you see a forest or a coral reef, remember, these things exist because life is stubborn. They're the end result of a long, slow climb back from the edge. Every tree, every animal, every bit of green is a sign that recovery is possible, even after the worst day Earth ever saw. But even with all we know, there are still mysteries. The rocks can only tell us so much. Some questions may never have clear answers. That's part of the story too. Science can show us the path, but some parts of the journey are still in shadow, and as we keep digging, searching and wondering, the story of recovery after almost total loss keeps unfolding. So, we've traced the recovery. We've talked about how life came back, slow, uneven, surprising, but the truth is there are still huge blank spots in our picture. Even after all the digging, testing and modelling, some of the biggest questions about this extinction are still out there. They hang over the story like a fog that just won't lift. Let's start with something basic. Why did this event hit so much harder than anything else? There have been other disasters in Earth's history. Big volcanoes, shifting climates, asteroids, but nothing else ever wiped out life so completely. Not before, not since. The Siberian traps were massive, yes, but other eruptions like the Deccan traps in India were also huge. Those didn't cause losses on this scale. So what made this one different? Scientists have tried to line up all the clues. They match up the timing of the volcanic eruptions with signs of warming, acid rain, and ocean changes. But the more closely they look, the more questions pop up. For example, the main phase of the Siberian traps eruptions lasted for about 900,000 years. But the sharpest part of the extinction, the kill zone, if you want to call it that, seems to have happened in less than 60,000 years. Some fossils suggest it may have been even quicker, maybe just a few thousand years. That's lightning fast in geological terms. So, did life just get unlucky? Was it a perfect storm of disasters? Or was something else at work? Here's one puzzle: the role of methane. Volcanoes put out a ton of carbon dioxide, yes, but methane is even more powerful as a greenhouse gas. There are signs that, around the time of the extinction, huge amounts of methane flooded into the atmosphere. Some came from the ground. Frozen methane in the Arctic, called methane clathrates, may have melted as the planet warmed. Other methane could have bubbled up from the ocean floor. But exactly how much, and how fast, that's a mystery. The numbers are hard to nail down. Some computer models show that if you suddenly dump a huge load of methane into the air, you can spike the temperature by over 10 degrees. That's enough to bake most life forms. But the rocks don't always tell the same story everywhere. Some places show signs of rapid warming, others seem more gradual, and there's always the question, did the methane really come from the clathrates? Or was it made by something else? Another mystery is the dead zones in the ocean. We know that low oxygen played a role, but why did the ocean lose oxygen so completely and for so long? Today the ocean has dead zones near river mouths or in places where too much fertilizer runs off the land. But these are small and temporary. During the extinction, the dead zones covered almost the whole ocean, and they stuck around for ages. Some scientists think the ocean may have flipped into a different state, one where bacteria that make hydrogen sulfide took over, poisoning the water and the air. But how did it get that way, and why was it so hard to reverse? And here's another thing. The rocks from this time sometimes show strange chemical spikes. For example, there's a big jump in certain forms of carbon and sulfur. These isotope spikes show that the whole cycle of life and death on Earth was out of whack. But what set off those changes? And why do they show up in some places and not others? That's still being argued in labs and conference rooms all over the world. Now let's talk about the survivors. We know some species made it through, but the real question is, why them? Some animals and plants that survived don't seem special. They weren't always tougher or smarter than the ones that died. In some cases, the survivors even lived in the same places as their extinct neighbours. So, what gave them the edge? One idea is that it was about being able to handle stress. If you could survive high heat, low oxygen, or dirty water, you had a better shot. But there are exceptions everywhere you look. Some tough, widespread creatures vanished. Some delicate ones hung on. Maybe it was just luck, being in the right place at the right time, or maybe there were hidden traits that we can't see in the fossils. There's also the question of how life first got a foothold again. We see that simple, fast-growing species often come back first after a disaster, but how did the more complex ecosystems rebuild? In some places, life seems to have started over with a few basic building blocks, then slowly added more variety. In others, there are weird false starts, where ecosystems begin to recover, then crash again. What caused those setbacks? Was it more volcanic activity, shift in climate, disease, maybe a mix of things we haven't even thought of yet? Here's something that keeps scientists up at night. Could it happen again? The conditions that led to this extinction were extreme, but some parts sound familiar. Rising carbon dioxide, changing climate, warming oceans. There are even small dead zones popping up today, especially near big rivers and along crowded coastlines. Is that a warning sign? Or are today's changes too small to compare? Nobody is sure, but the past does show us that, under the right or wrong set of circumstances, life can be pushed to the edge. Now, about the timing. The exact sequence of events is still a puzzle. Did the volcanoes kick things off, then methane made it worse, then the oceans crashed? Or did some things happen at the same time, feeding off each other in a spiral? The rocks hold clues, but they don't always line up neatly. In some places, the signs of disaster come before the main volcanic eruptions. In others, the worst changes show up after the biggest lava flows. It's like trying to read a book where half the pages are missing and the chapters are out of order. Some researchers have looked for clues in tiny crystals called zircons, which form in volcanic ash. These can be dated very precisely. If you line up the ages of the ash layers with the signs of extinction, you can try to build a timeline. But even the best data is fuzzy, with gaps and overlaps. That leaves room for debate. Another strange thing. Some groups of animals seem to vanish before the main disaster. In the fossil record, you see a slow decline in some species during the years leading up to the big event. Was this a warning sign? Was the world already stressed out, with ecosystems starting to unravel before the final blow landed? Or was it just a coincidence? Part of the normal ups and downs of life on Earth? Scientists are still arguing about it. Then there's the mystery of the coal gap. We know coal didn't form for a long stretch after the extinction. That means there weren't big, stable forests. But why did forests take so long to return? Was it just the bad climate? Or did something else, maybe changes in soil or fungi or some missing piece of the ecosystem, hold things back? We don't have all the answers. Let's zoom in on the deep sea. For a long time after the extinction, almost nothing lived in the deep ocean. Even after the surface waters started to recover, the depth stayed empty. Why? Was it a lack of oxygen? Or maybe something poisonous in the water? Some people think it might be about the way the ocean currents changed. If cold, oxygen-rich water stops sinking at the poles, the deep sea just sits there, getting more and more stale. But we can't go back and measure the old currents. All we have are hints in the rocks. Now, about volcanoes. The Siberian traps are the main suspect, but some scientists wonder if there was more going on. For example, what about asteroid impacts? No giant crater from this time has been found, but tiny grains of shocked quartz, minerals that form in big impacts, show up in some rocks. Are these grains proof of another disaster, or were they moved there by wind and water long after the event? The debate is still open. Another thing that's hard to figure out: why did some places get hit harder than others? In some regions, nearly everything vanished. In others, a few species slipped through. Was it about geography, climate, luck? Or maybe some places just had better refuges, spots where life could hide out until things calmed down. Today, scientists look for these ancient safe zones in rocks all over the world. Sometimes they find hints, like a layer with more fossils than usual, or signs of less damage from acid rain or heat. One theory is that places near the poles or at certain elevations might have been safer. Maybe the climate changes hit hardest in the tropics, but less in the far north or south. Or maybe some places just had better shelter, deep lakes, caves, or other spots that buffered the worst of the heat and poisons. Then there's the question of how quickly things could recover. Even after the worst was over, recovery was slow. But why so slow? Some people think it's about ecological inertia, the idea that once an ecosystem is broken, it takes a very long time for all the pieces to come back together. Others wonder if there were still problems, like lingering heat, toxic chemicals, or unstable weather, that kept knocking life back down. Let's look at the chemistry for a minute. During the extinction, the air was full of carbon dioxide. Oceans were more acidic than at almost any other time in Earth's history. Acid rain fell on land, wiping out plants and hurting soils. But how did all these changes interact? Was it the acid rain that killed forests? Or the heat? Or both? And why did some plants come back faster than others? Some researchers study ancient soil layers to find out. They look for signs of acid damage, like certain minerals that only form in low pH soils. These minerals show up in rocks from this time, but not everywhere. That means the effects were patchy, not global. Maybe some areas escaped the worst of the acid, and that's where plants started to recover. Here's another odd detail. In some places, after the extinction, you see huge blooms of algae in lakes and rivers. These algae covered the water, making it hard for anything else to live there. Some people think this was because there were no trees to hold soil in place. Rain washed dirt and nutrients into the water, and algae took over. It's a reminder that when you change one part of nature, everything else can shift in unpredictable ways. And then there are the missing fossils. For some time periods, almost nothing is preserved. That makes it hard to know what really happened. Did everything die, or did life hide out somewhere we can't see? Maybe there were creatures living in places where fossils don't form well, like high in the mountains or in deep water. The fossil record is like a patchwork quilt, with big holes where data is missing. Now think about the plants. We know certain types came back first. Ferns, small seed plants, things that can handle bad conditions. But what about the fungi? Some rocks from this time show a spike in fossilized fungal spores. This might mean there was a fungal spike, a world where, for a while, mushrooms and molds ruled the land, breaking down all the dead stuff. But how long did this last? And did it really happen everywhere, or just in some places? The evidence is thin. Another theory that comes up is about disease. When ecosystems break down, diseases can spread more easily. Did outbreaks of bacteria, viruses, or other pathogens speed up the extinction? It's hard to prove because diseases don't leave clear fossils. But some people think they could have played a role, especially when animals were stressed and crowded in shrinking habitats. Let's talk about sunlight. After the volcanoes erupted, the sky may have been filled with dust and ash. Some computer models say this could have blocked sunlight for years, causing volcanic winter. If plants can't grow, everything else suffers. But how dark did it really get? And for how long? The rocks give us clues, like layers full of soot or signs of cold-loving plants popping up. But it's hard to line up the timing exactly. And then there's hydrogen sulfide. This gas is deadly to most life. In the past, some scientists thought giant blooms of sulfur bacteria in the ocean belched this gas into the air, turning the sky purple and choking the land. But how much hydrogen sulfide actually made it out? And did it reach far enough inland to kill forests and animals? That's still being studied. One more thing. did the extinction happen everywhere at the same time, or did it roll across the globe like a slow wave? Some fossil beds show a sharp cut-off. Species vanish all at once. Others show a more gradual fade. Maybe the disaster started in one place and spread, or maybe it hit different regions in different ways. With so many missing clues, it's tough to say. So what does all this uncertainty mean? Does it make the story any less powerful? Not really. In fact, the mysteries are a big part of what makes this event so fascinating. Every time scientists think they've solved one puzzle, a new question pops up. It's like a detective story with more suspects than answers. And here's what gets me. Even with all of our science, our labs, our computers, our satellites, we still can't answer some of the most basic questions about what happened during those dark days. We have pieces of the puzzle, sure, but the full picture is still out of reach. Maybe that's because the Earth is just too complex, or maybe some secrets are lost for good, buried in rocks we'll never dig up. But even the gaps in our knowledge can teach us something. They remind us that the world is always changing, that nature is both tough and fragile, that survival can depend on things we don't even see. And as we keep searching, new tools and new discoveries might fill in some of these holes. Maybe one day someone will find a hidden fossil bed, or invent a better way to read the rocks. Until then, the end Permian extinction will stay partly in the shadows, a warning, a mystery, and a story that's still being written. This is where the science ends and the big questions begin. Why did it happen the way it did? What does it say about life's ability to bounce back, or not? And what can we learn for our own future? We may never pin down every detail, but that's okay. Sometimes the best questions are the ones that keep us thinking, even after the lights go out. So, let's step back. We've talked about rocks and volcanoes and ancient oceans, but when you zoom all the way out, you start to see just how strange and rare this event really was. It's not just about lava or lost species, it's about the deep history of life, the kind of story that only happens once in billions of years. And the more you look at it, the more it makes you wonder about luck, chance, and how fragile things can be, even on a planet as old as ours. Think about how long life had already existed before the disaster. By the time of this extinction, Earth had been alive for almost 4 billion years. There had been weird creatures crawling through the mud, giant forests, fish with armor plates, and forests of towering trees. Life had survived ice ages, asteroid strikes, and giant floods. Whole continents had moved and crashed together. But nothing, not even the huge asteroid that wiped out the dinosaurs later, hit as hard as the event we're talking about tonight. So, why was this one so severe? And why did it happen then, and not at some other point? Some people think it was just bad luck, a rare set of disasters stacking up at the worst possible time. Others see it as a turning point, a moment when life was forced to change, and the old ways just couldn't survive. Let's dig into the timing for a second. The end Permian extinction didn't just hit out of nowhere. Before it happened, the world was already changing. The continents had come together into a single giant landmass called Pangea. That meant there were huge deserts, long coastlines, and big swings in temperature. Plants and animals had started to change too. Some groups were spreading and doing well, others were fading away. In a way, the stage was set for something big to happen. Now picture this. For tens of millions of years, strange animals ruled the land and sea. There were giant amphibians, weird reptiles, and plants that don't even exist anymore. Some of these creatures survived earlier disasters. They'd weathered droughts, heat waves, and cold snaps. But when the disaster struck, it was different. It wasn't just one thing. It was a pile-up. Volcanic eruptions, runaway heat, poisoned oceans, and maybe more. Here's something wild. Some groups that had been around forever just vanished. Trilobites, for example. Those little armoured sea bugs. had survived for over 250 million years. They'd seen everything, from supercontinents breaking up to asteroid impacts, and then, during this event, they went extinct for good, gone, just like that. It's hard to even picture a world that's been around that long and then, suddenly, part of it just disappears. Let's talk about how scientists know all this. They aren't just guessing. They study rocks from all over the world. Sometimes they find layers of ash or clues in the types of minerals. Other times they look at tiny grains of pollen or slices of ancient tree trunks turned to stone. They use radiometric dating, a way to measure the age of rocks using tiny amounts of radioactive stuff inside them. That lets them line up events across the globe, even if the rocks are thousands of miles apart. But there's still a lot we don't know. For example, some places show signs of the disaster earlier than others. In one spot, the extinction looks like it happened fast, almost overnight. In another, it seems to drag on for thousands of years. That's part of what makes this such a tough mystery. The story changes depending on where you look. And then there's the question of deep time. Most of us can't really picture what millions of years feels like. It's just too big for our brains. But for this story, the scale matters. The disaster didn't just wipe out life quickly. It left scars that lasted so long you could fit the entire history of humans, every single thing we've ever done, into the gap that followed. Now let's talk about the clues left behind by plants. After the disaster, forests were mostly gone. For a while the land was covered in low, scrubby plants. Things like mosses and ferns. These are tough survivors. They can live in bad soil, handle weird weather, and come back after fires or floods. But big trees, the kind that make real forests, didn't return for ages. Scientists can see this in coal beds. Before the extinction, you get thick layers of coal, evidence of ancient swamps and forests. Afterward, there's a long gap. No coal, no big forests. It's like nature had to start over from scratch. Some people wonder if this missing forest period changed the rest of Earth's story. Without trees, the soil eroded faster. Rivers turned muddy. Nutrients washed into lakes and seas, feeding giant blooms of algae. That could have made it even harder for animals to return. It's a snowball effect, one disaster causing another, and so on. And what about the animals? On land, the survivors weren't the big, impressive ones. It was mostly small, quick breeders, things that grew fast and didn't need much to eat. In the sea, it was the same. Simple animals like clams, worms, and tiny crustaceans. The big, fancy creatures, giant fish, armoured reptiles, marine predators, were mostly gone. For a while, Earth was a world of underdogs. But here's what gets me. Even after all that loss, life didn't just give up. It adapted. It found new ways to survive. Some of the creatures that made it through would go on to become the ancestors of everything that came next. Without that reset, we might never have seen the rise of dinosaurs, or the first mammals, or eventually people like us. Let's look at the oceans again. After the disaster, the seas were weird places. In some spots there were giant mats of bacteria, slimy layers that covered the seafloor. These bacteria could handle low oxygen, and even poisons like hydrogen sulfide. For a while, they dominated. You can see their traces in the rocks, a thin black layer, sometimes full of certain chemicals or fossils of strange microbialites, which are basically ancient bacterial reefs. These bacteria weren't new. They'd been around since the earliest days of life, but for a time after the extinction, they took over again. It's almost like the clock got turned back. Life had to rebuild from the bottom up. Instead of coral reefs, you had these mats. Instead of big fish, small scavengers. And on land, the pattern was similar. The first animals to return in numbers were things like small reptiles, burrowing creatures, And those early mammal relatives, they lived short lives, had lots of babies, and didn't need much food. This is a trick you see after lots of disasters. Simple, fast-growing species come in first. Then, much later, things get more complex again. Now let's pause on the topic of deep time. It's easy to say 10 million years, but what does that really mean? If you lined up the entire span of modern humans, call it 300,000 years, it's still just a blip in that recovery. Imagine waiting 30 times longer than all of human history for forests to come back, or for the oceans to fill with big animals again. That's the kind of timescale we're talking about. And here's another thing. The disaster didn't just shape life. It also changed the planet itself. When forests vanished, the air changed. With fewer plants to pull carbon dioxide out of the air, the planet stayed hot. When rivers carried mud and nutrients into the sea, it changed the chemistry of the water. Even the shape of the land shifted as erosion sped up and new landscapes formed. Some scientists think this was the closest Earth ever came to becoming a dead planet. Not just a world with fewer species, but a place where the basic systems, air, water, soil, almost stopped working together. For a while, it was touch and go. If things had gone a little differently, maybe life wouldn't have bounced back at all, but it did. Slowly, step by step, the survivors adapted. New species appeared. Old ones evolved. Ecosystems got more complicated. It wasn't a straight line. There were setbacks, strange new disasters, and probably more than a few close calls. But over time, the world started to look alive again. Let's switch gears and talk about what this all means for us. We live in a world shaped by that ancient disaster, even if we don't notice it. Some of the plants and animals around today are direct descendants of the survivors. The way ecosystems work, the food chains, the way forests grow, even the shape of the continents, was set by what happened back then. And maybe the biggest lesson is that change isn't always slow. Sometimes things can shift fast. A stable world can become unstable in what, geologically speaking, is the blink of an eye. That's both scary and a little bit hopeful. It means that even the worst disasters aren't always the end. But it also means that balance is fragile. The story of the end Permian extinction is a story of loss, yes, but also of unexpected survival. It's about how, even when almost everything is gone, life finds a way to start over. The details are still being worked out. New fossils turn up every year. New theories are tested. Sometimes the answers surprise everyone. For example, some researchers are looking at how the event changed the evolution of life. After the extinction, new groups took over. In the sea, animals like ammonoids, spiral-shelled creatures, bounced back faster than anyone expected. On land, the ancestors of mammals slowly spread out, and the plants that came back weren't the same as before. The old forests never returned exactly as they were. New types of trees took their place. There's something powerful in that. It shows that even when the world feels broken, new things can grow. Life doesn't go back to the way it was. It changes. It adapts. Sometimes it even leaps forward. Now you might wonder, could something like this ever happen again? The answer is, nobody really knows. The conditions back then were unique, but some of the signs, rising carbon dioxide, warming, loss of oxygen in the ocean, are things we're starting to see today, though on a much smaller scale. It's not about predicting doom. It's about realizing how deeply connected everything is. Air, water, land, and life. And that brings us to a bigger point. When you look at the story of this extinction, you start to see that life isn't just tough. It's creative. It finds new paths. It builds new worlds out of the ashes of the old. There's a kind of deep hope in that. No matter how strange or empty things get, there's always a chance for a new beginning. So when you hear about these ancient disasters, it's not just a lesson in loss, it's also a lesson in resilience, in starting over, in trusting that, even when everything seems hopeless, a spark of life can survive and grow. And maybe that's what deep time teaches us, that nothing stays the same forever. Those disasters can open the door to something new, even if it takes a while to see it. That the world is always in motion, always changing, always surprising. We'll never know every detail. Some secrets will always stay buried. But even the mystery itself is part of the story. It's what keeps us looking, asking, and wondering. So, as you drift off tonight, think about this. You're part of a world that's been through more than we can even imagine. A world that's survived ice, fire, poison, and darkness. And yet, here we are, alive, still searching, still dreaming. That's the real legacy of the end Permian extinction. Not just the loss, but the comeback. The way life, against all odds, found a way forward. It's a story that never really ends. And that's something worth holding on to even in the quiet hours of the night. When you look back at everything that happened during this disaster, it's almost impossible not to be amazed. Not just at the loss, but at the way life pulled through. If you try to picture what it would have felt, like to live through that time, if anything could have lived at all, it's almost beyond imagination. The world before the disaster was packed with strange creatures, thick forests and busy seas. Then, in what feels like the blink of an eye, almost all of that disappeared. The survivors found themselves in a place that barely resembled the home they'd known. Now, if you're wondering why this story still matters, here's the thing. The planet we live on now is shaped by what happened back then. Our forests, our oceans, even the types of weather we get. All of it carries marks left by those ancient events. The lesson isn't just about what was lost. It's about the ways that life finds new footing, even when the old world is gone for good. Let's go back to the survivors for a second. After the worst was over, the world was filled with creatures and plants that were tough, quick, and flexible. The big, slow giants were out. The small, fast breeders were in. That pattern didn't just pop up during this disaster. It's something you see over and over every time the world gets shaken up. And that makes you think about how the rules of survival can shift at a moment's notice. But here's something even deeper. The way life came back wasn't just a repeat of what came before. It wasn't like hitting rewind and playing the same story again. New types of animals and plants took over. In the sea, creatures like ammonoids, those spiral-shelled animals, became the new stars. On land, the old forests never fully returned. New plants and new types of trees slowly took their place. It's almost like the world got a second chance to try out a different path. Why does this matter? Well, it shows that even the biggest disasters don't freeze the story. They just set the stage for something new. Sometimes the biggest changes come from the worst moments. When you zoom out far enough, you can see these turning points all through Earth's story. The old world falls apart. The pieces come together in new ways. Different winners and losers, different rules. Think about how scientists piece together all of this. They use tiny clues, bits of rock, fossils, the shape of old riverbeds, the dust trapped in ancient layers. These little details help build a picture of what changed and how long it took for things to shift again. It's never a perfect picture. There are always gaps. Some places hold more clues than others. But the more we learn, the clearer it gets that recovery is never simple or quick. If you step back even further, you see that the world isn't static. It's always in motion. Sometimes the changes are slow, almost invisible. Other times, It's like the ground drops out from under everything. The disaster we've been exploring is a reminder of just how quickly things can flip. What felt permanent was actually temporary. Stability can be an illusion. So what about today? It's easy to look at the far past and think it's got nothing to do with us. But the truth is, we're living with the results of those ancient disasters. Some of the animals and plants on Earth now are direct descendants of those early survivors. The shape of continents, the mix of life, even the chemistry of the air and sea, all of it is shaped by what came after the disaster. Scientists sometimes compare then and now. They look at the warning signs from the past: rising carbon dioxide, warmer climates, stressed oceans. It's not that we're about to face the same disaster, at least not on the same scale. But it does make you think about how connected everything is. Small shifts can add up. When you push a system too far, strange things can happen. It's a bit humbling to realise how fragile balance can be. Of course, there's another layer to all this. The fact that life came back at all is kind of a miracle. The world didn't just recover, it evolved into something new. There's a lesson in that. Even when things break, there's a chance for something better to grow in the cracks. That's not just true for ancient disasters. It's true for all kinds of change. What looks like the end is sometimes the start of something unexpected. There's a simple kind of hope in that. The world has been through more than we can even picture. It's taken hits that would seem impossible to survive. Yet here we are, living on a planet that's been knocked down, burned, flooded and frozen. And still, life goes on. Not the same as before, but still moving, still changing. Here's another thing to remember. The people studying these events aren't just looking for facts. They're trying to understand the big story. They want to know how life bounces back, what makes a system resilient, how patterns get broken and rebuilt. Every fossil, every layer of rock is a clue in a puzzle that's still being solved. Sometimes, when you think about deep time, it can feel overwhelming. The numbers are so big that they almost stop making sense. But maybe that's the point. Our lives are short, but we're part of something much longer. We're standing on the edge of a story that stretches back for billions of years. And somehow, we're the ones who get to look back, ask questions and try to make sense of it all. As you settle in, it's worth thinking about what it means to be part of a world that's survived so much. It puts even our biggest problems in perspective. The world changes, sometimes slowly, sometimes in bursts, and every time life adapts, shifts, and eventually finds a new path. So, what's the takeaway from this ancient disaster? Maybe it's this: nothing is set in stone. Even the worst losses can be followed by new beginnings. The planet's story isn't just about collapse, it's about recovery, invention, and the surprising ways that life keeps going. That's the heart of the story. Not just what was destroyed, but what came after. The strange new worlds that grew out of disaster. The survivors that set the stage for everything that followed, including us. If you ever feel like the world is too broken to fix, remember this old story. When almost everything was lost, the future was still possible. The comeback was slow, messy, and full of surprises. But it happened, and that's something worth holding on to. Even in the quietest, darkest moments, there's a spark of resilience waiting to be found. The story never really ends. It just keeps moving forward, one new chapter at a time.